Hey everyone, welcome back. So here's something I want you to think about for a second. What would it look like if an object from another star system started changing its structure while we watched? Not gradually over months, the way normal comets evolve, but rapidly, night to night. Geometric features appearing, shifting, flipping orientation entirely between observation sessions. Because that's exactly what an independent astrophotographer named Ray captured at 12,003 in the morning last night. And I've been staring at these images for hours, trying to make sense of what I'm seeing. This isn't some blurry smudge that could be interpreted 100 different ways. This is documented, crystal clear evidence that 3I Atlas is transforming right in front of our eyes in ways that don't fit any model we have. Before we go further, if you're finding this interesting, you can subscribe anytime and turn on notifications. We're going to be covering the Jupiter encounter extensively, and based on what I'm about to show you, that flyby might be even more significant than we thought. Look, you already know this object was strange. We covered the contradictions, the impossible activation timing, the structure that doesn't exist in any comet catalog. But all of that was leading up to this moment, to what Ray captured while most of the world was asleep. The object flipped. It completely changed its visual orientation between observation sessions. And before you think, okay, things move in space, that's just orbital mechanics, no, you don't understand. This isn't normal movement. This is geometric transformation happening way faster than it should. Ray's been imaging 3I Atlas every single clear night since closest approach. Same telescope, same location, same processing techniques. He's methodical about this. For weeks, the structure was consistent. Tail on one side, nucleus on the other. Predictable geometry night after night, exactly what you'd expect from a comet following a stable trajectory through the inner solar system. Then, suddenly, without any warning, the entire visual configuration flipped. Tail now on the left where the nucleus used to be, nucleus on the right where the tail used to be. The object appears to be moving in the complete opposite direction across the frame. First thought was equipment malfunction. Maybe he mounted the camera wrong. Maybe the tracking went haywire during the session. Maybe something in the stacking process broke and introduced an artifact. He checked everything. Star fields are normal. Background galaxies sitting in exactly the positions they should be. Every other object in the frame behaves precisely as expected. Only 3I Atlas changed, which means this is real. This is actual geometric reconfiguration happening to an interstellar visitor while we're watching it in real time. Now, NASA would tell you this is just perspective shift. Earth and the comet are both moving through space. The sun's in a different position relative to both of us. Viewing angle changed creates optical flip. Basic geometry. And yeah, okay, I get that explanation. That's how orbits work. But here's what's bugging me about that reasoning. The speed of this change is nuts. We're talking about visual transformation between observation sessions that are only days apart. For context, when you watch normal comets over time, their orientation shifts gradually over weeks or months as the orbital geometry slowly evolves. This happened fast, too fast, for just passive perspective change from our movement and its movement combined. And Ray noticed something else in these new images that's even stranger. The color is unstable. Some nights, 3I Atlas shows this intense green coloration, bright, vivid, unmistakable in the processed frames. Other nights it's muted, different hue, almost gone entirely. This isn't gradual fading as distance increases, which would make perfect sense. This is night-to-night variability that doesn't match any pattern we've documented in comets before. Green in comets comes from diatomic carbon, C2 emission. Standard stuff. We've seen it in hundreds of comets over the decades. When carbon molecules get excited by solar radiation, they emit light at specific wavelengths that our eyes and cameras perceive as green. Every amateur astrophotographer knows this. It's Comets 101, basic emission spectroscopy. But here's the thing about C2 emission. It's relatively stable. Once a comet starts producing it at detectable levels, the color stays consistent. Unless something dramatic changes, like distance to the sun shifting significantly, or a major outburst event disrupting the coma structure. Ray's using identical equipment every single night. Same telescope, same camera, same exposure settings, same processing workflow. He's not changing any variables on his end. The only variable is the comet itself, and it's changing color rapidly, inconsistently, in ways that don't match any documented behavior pattern for cometary objects. Could be atmospheric conditions affecting the observations from the ground. He checked that too. Ray's observing from dark sky country with minimal light pollution. He tracks atmospheric transparency every session religiously. Some nights are better than others, sure. That's just how ground-based astronomy works. But atmospheric effects don't create this kind of sharp color variability. They blur things, they dim things, they scatter light and reduce contrast. They don't make specific emission wavelengths appear and disappear randomly from night to night. Could be imaging artifacts from the stacking process where you combine multiple exposures. Also checked. Single frames show the same variability before any stacking happens. This isn't processing error. This is the actual object changing its emission characteristics between observation sessions. So what's causing it? Ray's got a hypothesis, and the timing is too suspicious to ignore. Right now, the sun has massive coronal holes open on its surface. You can't see these with normal telescopes because they only show up in X-ray and extreme ultraviolet wavelengths. Coronal holes are regions where the sun's magnetic field structure opens up and allows high-speed solar wind to stream out into space at incredible velocities, much faster than the normal background solar wind. These solar wind bursts are hitting 3I Atlas, and the timing of the color changes lines up remarkably well with when these enhanced solar wind streams would have reached the comet's position based on propagation calculations. Here's the hypothesis. What if the solar wind is interacting with the comet's gas in real time and changing the excitation state of the molecules? What if the intensity and composition of the solar wind at any given moment is directly affecting how much C2 emission we're seeing? That would explain the rapid variability. Solar wind isn't constant. It fluctuates based on conditions at the sun's surface. When a high-speed stream hits the coma, molecules get excited differently than during quiet conditions. When the stream passes and normal solar wind returns, emission characteristics change. The comet's underlying composition stays the same, but its visual appearance shifts based on external energy input from the sun's magnetic environment. Here's why this matters. If 3I Atlas is this reactive to solar wind conditions, it means the coma composition is fundamentally different from normal solar system comets in ways we haven't fully characterized. We've never documented this kind of dramatic color response to space weather before in any comet. Comets interact with solar wind, absolutely. That's how ion tails form in the first place. But rapid color changes visible in amateur telescopes from ground-based observations on timescales of individual nights, that's new. That's something we haven't seen, and it raises massive questions about composition. What molecules are present in that coma that make it so sensitive to solar wind interaction? Standard water ice comets don't behave this way. Carbon dioxide-dominated comets don't behave this way. So what's the actual chemistry here? The honest answer is nobody knows yet. Ray's documenting changes that don't fit our existing models, and professional astronomers don't have a comprehensive published explanation. They've got hypotheses about exotic ice compositions, different formation environments around other stars, unusual molecular structures we don't encounter in local comets. But actual spectroscopic confirmation identifying specific molecules, that data either doesn't exist yet or hasn't been made public. Ray's time series imaging is capturing something unprecedented. Every clear night, he's documenting not just where the object is positioned, but what it looks like, how its internal structure evolves, how its color changes over time. This is exactly the kind of monitoring that professional observatories should be doing with dedicated observation campaigns, but they're not. They're operating on their normal schedules, proposal-driven timelines, waiting for telescope allocation through the standard committee process. Meanwhile, Ray's out there at midnight capturing changes that are happening right now. Think about that for a second. An independent amateur observer with good equipment and obsessive dedication is producing data that major institutions aren't getting. Not because his telescope is better than theirs. It's obviously not, but because he can observe every single clear night without waiting for committee approvals or fighting for competitive telescope time. He sees something interesting. He images it immediately. He notices a change, he follows up the next night. That's how science used to work before everything got institutionalized into rigid scheduling structures. But the color weirdness is just the beginning of what these images show. When Ray stacks his data, combining about 77 minutes of total exposure time, something else becomes visible that you can't see in single frames. The inner coma has structure, and that structure is rotating. Think about what this means. Most amateur comet images show a fuzzy blob, maybe a visible tail, maybe some brightness gradient from the central condensation outward, but the core region usually looks like a smooth, featureless cloud. When you stack exposures to go deeper and pull out fainter detail, you just get a brighter, more detailed blob. That's what you'd expect from a relatively uniform gas and dust cloud surrounding a tiny, unresolved nucleus. Not with 3i Atlas. Stack the images and you start seeing geometry in the inner coma, brightness variations that aren't random, features that aren't evenly distributed around the center, structure that appears concentrated on one side and absent on the other. And between frames captured on different nights, that structure shifts position. It rotates. It moves in ways that can't be explained by tracking errors or atmospheric seeing conditions. Ray does comet-aligned stacks, meaning he tracks the comet's motion across the sky and keeps it fixed in the center of the frame while background stars trail into lines. In these stacks, the stars make perfect linear trails, proving the tracking is accurate and consistent. But the internal features of the comet itself, their shifting position relative to each other between sessions. Features that were on the left side move to the right. Bright regions become dim regions as something rotates into and out of view. The structure is evolving frame to frame. This is rotation. Real physical rotation of material in the inner coma, possibly reflecting the rotation of the nucleus itself underneath. And we're seeing it happen in essentially real time through a ground-based amateur telescope. Let me put this in perspective. Professional spacecraft missions to comets spend years planning observations specifically to catch and characterize rotation. The Rosetta mission orbited Comet 67P for 2 years, and part of that extended duration was specifically to study how the nucleus rotates and how that rotation affects cometary activity patterns. This is considered cutting-edge comet science, requiring dedicated space missions with billion-dollar price tags. And Ray's capturing similar rotational data from his backyard, documenting the rotation of an interstellar object that's tens of millions of kilometers away using equipment any serious amateur could acquire. The brightness distribution in the inner coma isn't uniform. There are concentrated regions, specific areas where emission appears stronger than the surrounding material. As the object rotates, these concentrated regions move in and out of our line of sight, which strongly suggests localized active regions on the nuclear surface. Specific spots where gas and dust are being ejected preferentially rather than uniform sublimation happening equally across the entire surface. This is exactly what you'd expect from a rotating nucleus with a few dominant jets. The sun heats one hemisphere, ice sublimates from active regions where it's exposed, jets fire material into space creating the coma. As the nucleus rotates on its axis, different active regions rotate to face the sun and Earth, creating the brightness variations we're documenting. Except here's where it gets complicated. The structure Ray's imaging is too coherent, too geometrically stable. Normal comets with multiple localized jets produce lumpy, irregular, chaotic comas. You see messy structure because multiple jets fire at different angles, interact with each other hydrodynamically, create turbulence in the outflowing gas. The coma looks disorganized because the underlying physics is disorganized. Ray's images show organized structure. The brightness variations aren't random noise. They follow geometric patterns that persist from night to night. There's symmetry here that shouldn't exist if we're just looking at chaotic jet activity from an irregularly tumbling nucleus. Which brings us to the most bizarre feature Ray's been documenting. The cone. In the inner coma, clearly visible in stacked images from multiple observation nights, there's this V-shaped cone-like structure, narrow, pointed, extending away from the nucleus region in a defined geometric shape. It's not the broad, flat dust fans that normal comets produce from distributed surface activity. It's not the irregular spray pattern you'd expect from chaotic, multi-jet activity. It's a defined geometric shape, a cone of gas that looks almost artificial in how precise and stable it appears. Ray's been imaging comets for years. He's captured dozens of different objects, knows intimately what normal comet structure looks like across different sizes and activity levels. He's never seen anything like this cone feature. And before you think this might be unique to his specific equipment or processing technique, other independent observers are seeing it too. Amateur astronomy networks have been comparing images. Different telescopes, different cameras, different geographic locations, different processing software. Same cone structure showing up consistently in everyone's data. More importantly, this geometry has been spotted in images from completely different observation platforms. Ray mentioned seeing similar structure in Mars orbiter data. Not images of Mars itself, but images that spacecraft orbiting Mars captured of 3I Atlas when it passed through their field of view during the close approach. Different instrument entirely, different orbital perspective, completely different imaging system and wavelength sensitivity. Same cone structure visible. So this isn't an artifact of any particular telescope or camera. This isn't processing error from a specific software package. This is an atmospheric distortion that would be unique to ground-based observation. Multiple independent observations from both ground-based amateur setups and space-based professional platforms are all showing the same geometric feature. The cone is real. Now, what causes it? There are two possibilities that make physical sense. Option 1, there's a single dominant active region on the nucleus surface. One massive jet that's firing way more material than any other region, dominating the entire coma structure. The gas expands outward in a focused stream, creating this cone shape as it spreads and interacts with solar radiation pressure and solar wind. You're essentially seeing one giant exhaust plume overwhelming everything else. That would be unusual for a comet, but not impossible. Some comets do have strongly dominant jets that produce asymmetric comas, but they're rarely this geometrically clean, this stable over time, this persistent across multiple observation sessions. Usually you see some irregularity, some wobble as the nucleus rotates, some indication that other, weaker jets are contributing to the overall coma structure. Ray's images show almost perfect V-shaped geometry. It's too clean. Option 2, and this is where it gets genuinely interesting from a physics standpoint, there are two jets firing from opposite sides of the nucleus simultaneously. If you've got active regions on opposing hemispheres and you're viewing the object approximately edge-on to that jet axis, those two opposing streams would create a cone-like appearance in projection. The geometry would look pointed and narrow because you're seeing both jets foreshortened into a single narrow profile from our viewing angle. This would explain the symmetry we're seeing. This would explain why the structure is so geometrically stable over time. Two opposing jets locked into the rotation pattern, firing continuously as the nucleus spins on its axis. From our particular viewing angle, it looks like a single cone structure, but it's actually two separate streams we're seeing superimposed in projection. The problem is, Ray's resolution isn't high enough to definitively determine which scenario is correct. You'd need Hubble Space Telescope, or maybe a really good adaptive optics system on a large, professional ground-based telescope to resolve the nucleus region clearly enough to actually count individual jets and determine their geometry. And as far as I can find from published literature, nobody's released Hubble observations of 3I Atlas showing this level of structural detail in the inner coma. So we've got documented cone structure, multiple independent confirmations from different observers and platforms, and no definitive explanation yet for what's creating it. Just competing hypotheses, waiting for better data to discriminate between them. You know what's really getting to me about this? I went through historical comet image archives. Ray did too, independently. We're talking about searching through hundreds of professional and amateur images spanning decades of comet observation. Comet Hale, BOP, Hyakutake, But not Lovejoy, every bright comet that's been extensively photographed and studied. And you know how many show this kind of narrow, pointed, cone-shaped gas structure in the inner coma region? 0. None of them. This geometry doesn't exist anywhere in the documented historical record of comet observations. Either this is the first time in human observational history that we're seeing this kind of structure in a cometary object, or somehow every professional observatory that's photographed comets over the past century missed it entirely. Given that Ray and other amateurs in the network are capturing it consistently with modern digital imaging equipment and processing techniques, I'm confident in option 1. This is legitimately unprecedented. And here's the important thing to understand. Unprecedented doesn't automatically mean impossible or artificial or evidence of something exotic. It just means we haven't seen it before. Which actually makes complete sense when you think about it carefully, because we've only confirmed 3 interstellar objects in human history. Total sample size of 3. Oumuamua was weird in its own ways, with that unexplained, non-gravitational acceleration and unusual shape. 2. Borisov was remarkably normal, looked and behaved exactly like a typical solar system comet. 3. Atlas is weird again, doing things we can't fully explain with current models. 2 out of 3 interstellar visitors have shown anomalous behavior that doesn't match our expectations. But that's not enough data to draw any meaningful statistical conclusions about what's typical for objects from other stellar systems. Maybe this cone structure is completely normal for comets that form around other stars with different chemical compositions. Maybe the physics or chemistry that creates it is common throughout the galaxy, and rare only in our particular solar system's comet population. Maybe our local comets are actually the weird outliers and we just don't realize it, because our entire reference frame for what comets should look like is based on a single stellar system, but without detailed spectroscopy showing exactly what gases are present in that cone structure, without composition analysis confirming what specific molecules are being ejected and in what ratios. We're limited to educated guessing about what the actual composition might be. And our critical spectroscopic data either doesn't exist yet or hasn't been made public by whatever professional teams might have collected it. Meanwhile, the object is fading. Ray's latest images show it's definitely dimmer than it was even a week ago. Still visible, still showing that internal structure, but the signal-to-noise ratio is degrading noticeably with each passing night. Every day it gets further from the sun, further from Earth, harder to observe with any given telescope. The observation window is closing in real time while we watch. And where is it heading? Straight toward Jupiter. Not in a vague, might interact eventually way, in a this trajectory definitely passes through Jupiter's gravitational sphere of influence way. The orbital calculations are clear. The velocity is extraordinary. And sometime in the coming months, 3I Atlas is going to skim past Jupiter's gravity well. It's moving way too fast to be gravitationally captured. Jupiter's immense gravity isn't going to slow it down enough to trap it into any kind of orbit around the giant planet. This is a flyby event, not a capture event. But flybys still have physical consequences. They perturb trajectories in measurable ways. They can stress internal structures through tidal forces. They might even trigger new outburst activity if the gravitational gradient across the object is strong enough to crack surface layers or expose fresh volatile material. Ray's planning to keep imaging it as it approaches Jupiter. If something changes during that encounter, if new activity starts, if the structure morphs when it enters Jupiter's gravitational influence, he'll document it. Assuming it's still bright enough to photograph meaningfully by then, which is becoming a genuine concern as it fades. Professional observatories should be coordinating comprehensive observation campaigns around this Jupiter encounter. This is a one-time opportunity in human history to watch an interstellar object interact gravitationally with the largest planet in our solar system. We've literally never seen this before. We have no idea what might happen, and the data from such an encounter could tell us enormous amounts about the object's composition, internal structure, and physical properties. If Jupiter's tidal forces trigger outbursts, we learn something about the structural strength of the material. If the trajectory changes by measurable amounts during the flyby, we get better constraints on the object's total mass. This is valuable science just sitting there waiting to be collected by anyone pointing a capable telescope in the right direction. But as far as I can determine from published observation schedules and announced programs, there's no major coordinated multi-telescope campaign being organized around this encounter. Individual facilities might be planning their own observations, absolutely. But there's no public announcement of a comprehensive multi-wavelength effort, no coordination between space-based and ground-based assets, no emergency observation proposals getting fast-tracked through the normal bureaucratic allocation processes. Which means we're probably going to watch this unprecedented event with scattered observations from whoever happens to be looking at the right time with the right equipment, rather than a systematic, coordinated campaign designed to extract maximum scientific value. And then 3, iAtlas will keep moving outward, keep fading as distance increases, and eventually disappear from observational reach entirely, gone forever, carrying whatever answers it might have provided about interstellar object behavior, composition, and physical properties out into the void where we'll never be able to study it again. Ray's work matters precisely because of this institutional gap. He's creating a time-stamped visual archive documenting how 3i Atlas evolved during and after its closest approach to Earth. Every image is proof that the object was still showing interesting, scientifically valuable structure. Every night of observations is documentation that the window was open and someone was actually using it to collect data. Years from now, when scientists look back at this encounter and try to piece together what happened, Ray's images are going to be part of the historical record. They'll appear in papers, in databases, in comparative studies when the next interstellar object shows up. Because this is how science actually advances sometimes, through dedicated individuals documenting phenomena that institutions don't have the flexibility or resources or scheduling bandwidth to prioritize properly. Let me be very clear about something, because I know how these discussions tend to go. Ray is not claiming this object is artificial. He's not suggesting intent or design or spacecraft or any of that. He's explicitly clear about this in every discussion of his observations. He's an astrophotographer documenting what's visible through his telescope. That's the entirety of his claim. The observations themselves are strange enough without adding speculation on top, but the observations genuinely are strange. That's just factual, based on the documented evidence. An interstellar visitor showing rapid night-to-night color variability, rotating internal structure, visible in stacked exposures, unprecedented cone geometry that doesn't appear in any historical comet observation record, activation timing that contradicted earlier spectroscopic measurements. These are documented observational facts confirmed by multiple independent observers, not speculation or interpretation. And strange observations are exactly where scientific discovery happens. When things don't fit our existing models, that's precisely when we learn something new about how the universe actually works. When observations contradict predictions, that's when we're forced to update our theoretical understanding. The problem isn't that 3i Atlas is weird. The problem would be pretending it's not weird when the data clearly shows otherwise. Here's what we actually know from confirmed observations. 3i Atlas came from outside our solar system. That's confirmed definitively by trajectory analysis showing hyperbolic orbit. It showed no detectable cometary gases in pre-perihelion spectroscopy. That's confirmed by very large telescope observations taken before closest solar approach. It activated and developed a visible coma after perihelion despite having no detected volatiles before. That's confirmed by brightness measurements and visual observations from multiple sources. It produced X-ray emissions indicating the presence of gas in the coma interacting with solar wind. That's confirmed by JAXA satellite data. It now shows rotating structure and cone geometry visible even in ground-based amateur images. That's confirmed by Ray and multiple other independent observers. Those facts don't fit together into a coherent, simple narrative. Either the VLT somehow missed gases that were actually present, or the object manufactured or exposed gases that genuinely weren't detectable before, or the X-ray detection mechanism works differently than our models predict. Something in that chain of observations isn't matching our current theoretical frameworks for how comets behave. And now we've got the color variability and rapid geometric changes. More observations that don't fit standard comet behavior patterns. More data points suggesting this particular object operates under different physical or chemical rules than what we're accustomed to seeing in solar system cometary bodies. The composition has to be fundamentally different from typical comets. That's really the only explanation that makes all these diverse observations simultaneously possible. If the ice composition is dominated by molecules we don't normally encounter in significant quantities in solar system comets, that could potentially explain the spectroscopy contradictions. If there are exotic volatile compounds that sublimate at different temperatures or respond to solar wind in unusual ways, that could explain the activation timing and the color variability. If the internal structure has physical properties we haven't encountered before in studied comets, that could explain the geometric features. But without detailed spectroscopy taken during this active phase while emission lines are still strong enough to detect and identify, we're limited to educated guessing about what the actual composition might be. And time is running out to collect that critical data. The object fades more every day. Soon it'll be too dim for meaningful spectroscopic observations. The emission lines will be too weak to detect above background noise levels, and we'll be permanently stuck with whatever observations were collected during the bright phase, trying to reverse engineer explanations from incomplete information. This is exactly what happened with Oumuamua. By the time the scientific community fully realized how genuinely weird that object was, by the time observation proposals got written and submitted and reviewed and scheduled, it had already faded too much. We missed the critical observation window, and now we're stuck in endless, unresolvable debates about nitrogen icebergs versus light sails versus other exotic hypotheses, precisely because we don't have the data that would definitively distinguish between competing explanations. We're watching the same pattern unfold with 3I Atlas. Rays documenting that the object is still active, still showing interesting structure, still bright enough to study meaningfully, but the comprehensive multi-wavelength professional campaigns that would actually answer the composition questions definitively, those aren't happening fast enough to catch the window while it's still open. Maybe I'm wrong about the institutional response. Maybe there's a massive coordinated observing program running behind the scenes that simply hasn't been publicly announced yet. Maybe every major professional telescope is actually collecting 3I Atlas data right now, and we'll see comprehensive papers published in a few months that explain everything we're currently puzzling over. But based on what's actually been published so far, based on the absence of major public announcements, based on how these institutional processes normally work in practice, I'm not optimistic that's happening. The reality is that interstellar objects should automatically trigger emergency observation protocols. They should immediately jump to the front of every telescope queue. They're scientifically rarer than supernovae, more valuable for understanding planetary system formation than most routine observation programs, and they don't ever come back. Once they're gone from our solar system, they're gone forever. The data we collect during their brief passage is the only data humanity will ever have about that particular object. But astronomical institutions aren't structured to respond that way to this category of target. There are established procedures, committees, allocation schedules, proposal review timelines. Emergency observation protocols exist for specific event types like gamma-ray burst afterglows or hazardous near-Earth asteroid approaches. Events that have established response frameworks built up over years. Interstellar objects are too new as a phenomenon, too rare in occurrence. The protocols for rapid response simply don't exist yet in most institutions, so they get observed when telescope time becomes available through normal channels, which means we systematically miss critical observation windows because our organizational systems aren't designed for transient visitors that don't wait for committee schedules. Ray doesn't operate under those constraints. He sees something scientifically interesting. He observes it that same night. He notices a change in the data. He follows up immediately the next clear night. That flexibility, that ability to respond in real time without institutional approval chains, is the fundamental advantage of independent citizen science observation. The cone structure in Ray's images is genuinely publication-worthy as an observation. If that same feature showed up first in Hubble Space Telescope data, it would be in Nature or Science within weeks. Unprecedented geometric structure in interstellar comet coma would be the headline. Major discovery. But because it's appearing in amateur data first, documented by independent observers rather than professional institutions, it's getting far less attention than the scientific significance warrants. Ray's not trying to publish in prestigious journals. He's not chasing academic credentials or citation metrics. He's simply documenting what's visible through his telescope because it's genuinely fascinating and because no one else is doing it with this level of dedication and consistency. That's citizen science working exactly as it should, filling observational gaps that institutional science leaves open due to structural limitations. The object is still out there tonight, still visible if you have decent equipment and dark skies, still showing structure if you stack enough exposures to build signal, still changing if you watch it consistently night after night. This isn't abstract theoretical discussion. This is happening right now in our solar system in real time, an actual visitor from another stellar system passing through our cosmic neighborhood. And anyone with the right equipment and skills can participate in observing and documenting it. That's genuinely remarkable when you stop to think about it. We're living through historical moments that will appear in astronomy textbooks decades from now. First confirmed interstellar object. Second one. Third one. These are discovery events that define eras in astronomical history. And we're not just reading about them after the fact. We're watching them happen. We're collecting data. We're part of the observation and discovery process as it unfolds. Ray understands that deeply, which is why he's been so obsessive about consistent documentation. This is history being made, and his images are becoming part of that historical record. Years from now, when we have better theoretical frameworks for understanding interstellar object composition and behavior, when we've observed dozens more of these visitors and can identify patterns, researchers will look back at these early observations and analyze them with context we don't currently possess. They'll see the cone structure. They'll see the color variability. They'll see the rotation signatures and the geometric changes. They'll have Ray's time series showing exactly how this object evolved day by day during its passage through our inner solar system. And maybe by then, we'll understand what we're actually looking at. Maybe future theoretical advances will make it all obvious in retrospect. Maybe scientists in 2040 will read about 3I Atlas and think, of course it behaved that way. That's exactly what you'd expect from a nitrogen ice-dominated interstellar comet formed in a metal-poor stellar environment with those specific formation conditions. Or maybe it'll still be mysterious even then. Maybe even with decades more observations of other interstellar objects providing comparison data. 3I Atlas will remain a genuine outlier, the weird one that didn't fit emerging patterns, the one that did things we still can't fully explain even with better data and better theories. Either way, the observations being collected right now matter enormously. The documentation matters. What Ray's capturing every clear night matters, because it's the only data we're ever going to have from this particular visitor. Once it fades beyond observational reach and continues its journey out of the solar system, there's no going back for better observations. No do-overs with improved instruments, no second chances. This is humanity's one and only opportunity to study this specific object, and Ray's making sure we have at least some comprehensive coverage, even if major institutions aren't providing it at the level the scientific opportunity deserves. The cone is real. The rotation signatures are real. The color changes are real. The geometric flip between sessions is real. Multiple independent observers confirm the unusual structure. The contradictions with earlier spectroscopic observations remain unexplained. And the object is heading toward its Jupiter encounter while simultaneously fading into the distance with every passing day. That's where we are right now. An interstellar object doing things we don't fully understand, documented by dedicated observers who are putting in the work night after night. While the window to learn more closes gradually but inexorably frame by frame as the object recedes into the outer solar system. And here's what I keep thinking about. In a few months, 3I Atlas will reach Jupiter. It'll pass through the gravitational field of the largest planet in our solar system, moving at speeds we can barely comprehend. And then it'll keep going, out past Saturn, past the Kuiper Belt, into the void between stars, gone forever. But what happens during that Jupiter flyby? Does the gravitational stress crack something open? Does new activity begin? Does the structure change in ways we can't predict? We genuinely don't know. Nobody does, because we've never watched an interstellar object interact with Jupiter before. This is completely uncharted territory. Ray's going to be watching. His telescope will be pointed at those coordinates every clear night until the object fades beyond his ability to image it. And whatever happens, he'll document it. The question is, will anyone else be watching closely enough to catch what comes next? I guess we'll find out.